Good evening and welcome to Monday Night Calculus. My name is Curtis Brown and I have Steve Kokoska and Tom Dick hanging out here with me, ready to get our calculus on this evening. Steve's got some great questions lined up for us. Tom's got some good calculator tips and tricks and things that you need to know. So I'll let them get started.
Well, thank you very much, Curtis. If you would be kind enough to let me share my screen.
I will be kind enough to let you share your screen. Let you do that. I forgot to do that before we got started. You should be able to do it now.
All right, looks pretty good. Let me see if I can make this full screen. We'll be looking good. Hang on one second here. Where the heck did it go? Oops. Let's try that again. There we go. Cheapers, where did it go?
Uh-oh.
Uh-oh, boy, let's see here. What's going on? Well, let's try this. Let's do this. We'll move that one. And tell me if you can see that now. Is that okay?
I can see it. It looks
all
good.
Right, fantastic. All right, well, as we begin tonight, Curtis, this is one of my favorite topics, volumes of solids of revolutions. This is just a very nice application, I think. And just a reminder as we begin this, that we do post these problems on the TI website, and we also post these on the Facebook page for AP Calculus teachers. And of course, we give you, Curtis and Allison, a little heads up. So we'll be asking you some questions on solving these problems tonight, too.
I'll do the best I can, Steve.
All right, good. I know you've had a harrowing day, but
if I miss something or whatever, I can always count on a few of the teachers out there to bail me
help you out. All right, here we go. Yeah. So I'm going to do a couple of basic, I think, volume problems, and then we'll get into a couple of more complex problems. And I apologize ahead of time, Curtis. I'm going to impose some of my notation or way that I solve these problems, and many out there may have a better way. But I'll show you how I attack these, some tips that I think make solving these a little bit easier. So let's try this one. Find the volume of the solid obtained by rotating the region bounded by the graphs that are given, or the graphs of the given expressions, excuse me, about the specified line. So in part A, we have y equal e to the minus 2x, y equals 0, x equal 1, and x equal minus 1. So the very first thing I'm going to try to do here is to draw this region that I want to revolve this time in this problem about the x-axis. So I've tried to do that, and I've shaded in the region in blue. And here's a couple of things that I notice and that I do and notice right away. So the first thing I see here is that the axis of revolution, which is the x-axis, forms what I call a bounding curve on the region. Since that's true, that says to me that this is going to be a problem solved by using the disk method. Now, the second thing I want to think about is, am I going to be integrating with respect to x or with respect to y? And so what I generally do is I pick out an arbitrary value x in or over the interval in question here, -1 to 1, and I draw an arbitrary radius. So I draw a radius of one of these disks that I'm going to revolve around the x-axis. And I notice that that radius is perpendicular to the x-axis. And since it is, that says to me that this is going to be a dx problem. I'm going to be integrating with respect to x. So all of that I do before I even try to set up a definite integral, all part of my sort of problem-solving technique here to make these a little bit easier. So let's see if I've got this right. The volume here would be pi times the integral from -1 to 1. How does x vary over the region of interest? And I'm going to scribble a little bit in here, Curtis, times r squared dx. What's the radius? Well, the radius is this distance from here to here at an arbitrary point x, and that's just e to the -2x. That's this height, e to the -2x. And I need to square it. Okay, so I go through a little bit of simplification here. Be careful, this becomes an e to the -4x over here. And because we're all really good at this integration, and this is an application type problem, I'm going to skip a couple of steps, but I might ask a question or two. How do you integrate this one? I know the lag time is a little bit long tonight, Curtis, but let's put that question out there just to get students and teachers thinking a little bit. What's the technique to integrate that? I notice here out in front, as I found an antiderivative, a negative sign appears, and there's a 4 down there in the denominator. Sort of makes sense if you think about this. This is actually a U substitution problem.
I was just going to say, that looks like a nice U substitution opportunity.
Beautiful, beautiful.
And you'll note that that did not come from the chat. That was purely from
you?
Up here.
Oh, very good. Very good. Very good. I don't mean to sound surprised. I apologize.
Come on.
Okay. So there's a minus and there's a 4 in the denominator. I have to evaluate this expression at 1 and -1. And don't let me make a mistake here. I plugged in the 1 up in the exponent there. I have a -4. The -1 gives me a 4. You'll notice what I did is I carried through that minus sign, multiplied through, and there's the exact, I think, symbolic answer. And you know that in AP Calculus, sometimes these problems are calculator active. And so I wrote this with 3 digits to the right of the decimal. I didn't use any units here. That seems like it's an awfully big number to me for the volume of this solid, but I think everything's right there. Tom is going to show you in a minute or two some other ways to visualize these solids, but here's a way to do it. Curtis, you and Tom both know that I like to use Mathematica. And so I produced this sort of representation of this solid using Mathematica. So you can almost see the x-axis in here running down the middle of this. And I'll try to add that in future figures. And I've rotated this region about that x-axis to form this solid. That's not bad. That's not a bad picture. Well, good. I'm going to try one more, Curtis, and then I'm going to let Tom try a couple of things on technology. So let's try this one. I think this works out kind of nicely. Here's the curve, or the expression for the curve. Y equals 1 divided by the square root of x squared plus 1. You might just think for a second or two about what the domain of that function is. The region is bounded by that curve, y equals 0, x equal -2, and x equal +2. And I want to revolve that again about the x-axis. So my region I've got here marked, shaded in blue. And once again, the x-axis forms a bounding curve for this region. And so I know that I'm going to be using the disk method. I pick an arbitrary point x over the region of interest, -2 to 2, and I draw in the radius of that disk. And I think a little bit about, well, what's the length of that radius? Well, it's just the height of the curve, 1 divided by the square root of x squared plus 1. The radius here is perpendicular to the x-axis. And okay, if I were doing this in class, I would write out, I have a little bit more time, I'd write out some things like this, kind of cryptically, but I would write r is perpendicular to the x-axis. And that tells me that I'm going to be integrating with respect to x. So, okay, let's see. Oh, you know what? I'm going to use a little symmetry in this one. I can see that this region over here is the same as that one. So I'm just going to find the volume from 0 to 2. And then I'm going to multiply by 2. So there's the 2 out in front. This is pi times the definite, and it'll go from 0 to 2 times the radius squared. Pretty cool. I probably should have parsed this a little bit differently so that I could ask a question or two. But there's the 2 pi still out in front. If I square that integrand, I think I've got a 1 divided by x squared plus 1. And of course, I gave it away here. But how do you integrate this one? How do you integrate that? Well, that's an integration just about by inspection. That's an arctangent.
Yep.
So let's see. I've still got the 2 pi out there. Did I do this right? I think so. here's the 2. What's the arctangent of 0? Well, that's just plain old 0. And I don't know, I kind of think this is kind of cool as we all enjoy mathematics. This is the exact symbolic answer for that volume. And I believe that works out as an approximation to 6.956. One little thing here, Curtis, that just dawned on me. As we write out these problems, we usually use an equal sign in AP Calculus, but we all understand that this value and this one aren't exactly equal. And on the AP Calculus exam, we're not too picky about these equal or approximation symbols in this type of a problem. If a student were to do this, we tend to be only picky about the equal signs. I think we've talked about this before when we talk about Taylor polynomials. So we all understand as mathematicians what we're doing in AP Calculus. We know that those two expressions aren't really equal, but for simplicity, because we're among friends, we use an equal sign. And here's a Mathematica rendering of what the solid might look like. You can kind of imagine the x-axis running down the middle of this, coming out here. I didn't have the opportunity in this particular figure to kind of shade that in over there. That should be a solid, but that gives you an idea about what this might look like in 3 dimensions. That's not too bad. This volume to me, again, seems kind of small in this case, but look at the scale here. Look at how X varies, look at how Y varies. Whoops, let me go down a little bit. And as you think about this a little bit, okay, 6.9 or 7 seems reasonable. All right, pretty cool. Before I try the next one, I think I'm going to hand this over to Tom. He's going to try a little bit with technology.
Sounds good.
There you go.
Okay, we'll give this a shot. See if it works all right. So you all can let me know if my TI-Nspire screen's coming up okay for you.
Yep, we can see it just fine. Thanks, Tom.
Looks good.
Great. So certainly 3D graphing is not part of the AP course description at all. But as a teacher, this is a place where you might want to make use of a 3D grapher just to give your students a chance to visualize or help them visualize what these solids of revolution actually look like. So if you want, you could view this as kind of a recipe for doing that, but it's good to think through the mathematics. So a way you can use a 3D grapher, and there is one on, it's not a 3D grapher unless you have a special program for it on the 84, but there is a built-in 3D grapher on Nspire, and there's other 3D graphers out there. Steve just mentioned Mathematica's got a nice one. But on your handheld, there's a 3D grapher on the Nspire. You don't have to have a CAS version to do that. But this one's a CAS version, but this is also on the regular TI-Nspire. And basically, the idea is to graph this. We're going to make use of a parametric plot. And what I'm assuming here is I've got a function y equal f of x. And I'm assuming the function is positive over this interval, a less than or equal x less than or equal to b. And that's the interval that I'm going to rotate this graph around the x-axis. And to visualize that, we're going to use the parametric plotter. And this is just the notation that Nspire uses for a parametric surface where you got a surface in 3 dimensions where each coordinate, x, y, and z, and the p is for parametric, is in terms of 2 parameters, t and u. It's a surface, a 2-dimensional surface in 3-dimensional space. And the idea behind it's pretty simple. We're just going to let x coordinate be defined by t and let t run from a to b. So that's just like our regular x variable. And then f of t, to get the circle that's traced out as you rotate around the x-axis, we'll take f of t as our radius. And this is the normal idea when you're plotting a circle parametrically. You take the radius times cosine, radius times the sine, get a circle in the xy plane if you're plotting parametrically. but we're going to be in the YZ plane. So we're actually coming out, and in viewing this, it's kind of like we're viewing the Z axis coming out toward us. Okay. And notice the U is going to run from 0 to 2 pi, so we get the full circle. Well, let's see how this works with the problem Steve just was looking at. And cross my fingers, we'll see if it actually works. All right, so I'm going to go to the next page here. And I see a regular old graphing page. So I really want to change that. So let me go to my menu. And you might think, okay, this is going to be under graph entry edit, but it's not. It's actually under view. Okay, so graph entry edit is for all your two-dimensional plots. If you go up to view, you can see we got 3D graphing as a possibility. So let's do the 3D graphing. And right now, this is set up to plot Z as a function of X and Y. And that's something you commonly see in multivariable calculus. Let me go over here to the side here, see what we can do. Or let's see, let's go back to the menu and the 3D graph entry. Okay, it was on function. I'm going to do parametric. Okay. And now we see, let's see. Oh, there's some stuff in there already. This is actually set up. Well, it's got the sine and cosine interchange. Let me go ahead and change this to what we were looking at. I think, Steve, your function was 1 over square root of x squared plus 1.
That's in B, yeah. So you're going to try A first, or you want to try
I think
B?
I'll go ahead and try part B. That's
okay. Yep, that was 1 divided by the square root of x squared plus 1.
Okay. Now we're letting x be t, so I'm going to put let me put cosine. Oops, my finger's on the wrong key here. There we go. Cosine of t, or excuse me, cosine of u.
Yep.
Times 1 divided by the square root of 1 plus p squared.
Perfect.
Oh, already plotted something, so let me go back. There probably was some function stored in f of t. So let me get my z. Now I'm going to do the same kind of thing here. I'm going to do sine of u times that 1 over square root of 1 plus p squared. All right, and there's my plot. I'm thinking that it's probably my domain is not the right domain. So let's take a look at that. See, let's go over here to the side. Let's do this dot, edit the parameters. Ah, there we go. So T-min, I think yours ran from -2 to 2, is that right?
Yes, correct.
Okay, so I'm going to let my T's run from -2 to 2. So your T range will be whatever your X interval is.
Gotcha.
And the U values, we want to do a full circle. You can see the default here is, I think, is 0 to pi. We're going to want to make that 0 to 2 pi. And all right, there we go. And I think that's looking like that surface that you plotted there. We can enlarge that a bit, I believe. Let's see if I can go back to my menu. We got range and zoom, range settings. I'm going to make my X-min be -2 to 2. And
while you're doing this, Tom, is the default here usually -5 to 5, or is that the default?
I think so.
That is the default.
-5 to 5 in all 3 directions, X, Y, and Z. So it gives kind of a cubical box here. All right, let's give it, let me make my Z also -1 to 1.
Yep, that should work.
And I am using some forecasting here that I know that the maximum value of that function. Oh, that's a lot better.
Yeah, that's pretty
Yeah,
cool.
there we go. And you can actually rotate this around. Now I'm doing this on a computer with the emulator. I don't know kind of how quickly this responds on the handheld, but you really do get a nice looking graph. And that's just a standard way that you can plot surfaces of revolution and get a nice picture to go with your analysis of the problem. So I think from a teacher's point of view, I like it for generating those pictures so students have some notion of what these animals are, these solids of evolution. And so it's pretty handy. Now you can definitely do, and I know, Steve, you've got some problems, not to let the cat out of the bag, you've got some problems where we rotate around the y-axis or rotate around some other line.
Yes.
You can still handle those, but you've got to be a little bit, you got to think through kind of how you want to adjust those, that setup, but it's definitely doable.
Possible. Okay.
So I think with that, I'm going to turn it back over to you, Steve.
Okay.
You're getting a comment here. Steve starts sharing again. We saw some comments about the visualization there, Tom, and that being a really nice one. That was cool. That was really neat to see on an Nspire handheld.
Yeah, right.
Be able to see that.
Okay. Well, let's try this one, Curtis. Let's see if we can do part C.
Okay.
So here the curve is y equal to cosine of x, kind of a familiar one, bounded by y equal to cosine of x, y equals 0, between minus pi over 2 and plus pi over 2. But this time we want to revolve this region about the line y equal -1. So as usual, I'm going to start out here with a drawing with an illustration and see if I can figure out what's going on, show you how I do some of these. So let me add in a little bit here. This blue curve is, of course, y equal to cosine of x. And down here, this horizontal line is y equal -1. The region of interest is shaded in light blue. And notice now, in this particular case, the axis of revolution is not a bounding curve. So that suggests to me that I'm going to have to use washers in order to do this one. And that also suggests to me that I'm going to need an outer radius and an inner radius. So I'm going to sneak off to the side here and just remind myself, how do I find the volume here? Pi times the integral from a to b of r sub o squared minus r sub I squared with a dx on the end. Okay, a little bit looking ahead, I can see that my radii are perpendicular to the x-axis, so I know this is going to be a dx problem. So I don't want to write this down, but Curtis, what do you think is a common error here for students rushing to do the exam? What do you think what sort of a mistake do you think they make in writing that integrand? R sub o squared minus r sub I squared. What's a very
they may not have good notation on their radii.
That's true. That's very true.
It would be something I would be tempted to make a mistake doing.
Okay. What do you think they do with that square frequently?
Oh, they just drop it on the outside instead
They just drop it on the outside. They take r sub o minus r sub I quantity
by r squared, right?
Yep. There you go. There you go. So don't make that mistake as this exam is coming up. That's a common error.
Look at that. Wanda and Mark coming through to help me out with that one.
Okay, very good. All right. Well, I need two radii. Again, my axis of revolution is y equal -1. So the outer radius I've got labeled here, the inner radius I've got labeled, and I need expressions for those lengths. So let's see. Oh, you know what? I also see some nice symmetry here in this region. So I'm going to put a 2 out in front once again, and I'm going to go from 0 to pi over 2. And let's see, what's the outer radius? Well, the outer radius, I'm sorry, Curtis, I'm going to scribble since I'm working over on this side. It would be that distance right there. That's a perfectly straight line. And let's see, what is that distance? Well, let's see, at an arbitrary point x, up here I'm at cosine of x, so cosine of x minus a -1. I'm finding the distance, the length of that outer radius. So there it is. There's the outer radius. And the inner radius is pretty easy. It's constant. It's just 1. So minus 1 squared.
Yeah.
Well, where possible, I'm going to do a couple of these, Curtis, analytically, not all of them, but where possible, and maybe you can help me a little bit with some of this. So I expanded this out. There we go. And I see that my 1's cancel. Let's see what I do in the next step here. What did I do? There's the 2 cosine of x. And then I guess I used a half angle formula. That's a pretty common, not trick, technique here to integrate cosine squared. Let's see, did I get this right? There's the 1/2. I multiplied through by the 1/2. And then actually I can integrate term by term with, okay, there's a little substitution in here with u equal to 2x, but it's almost integration by inspection. And so I end up with this antiderivative that I need to evaluate at pi over 2 and 0. Gee, I think I can do the 0 part. That looks pretty easy. So plugging in a pi over 2, let's see if I got that. 1/2 times pi over 2, 1/4 sine of pi. Yep, I think that's okay. So let's see, the sine of pi, that's 0. Sine of pi over 2 is 1. So I've got a 2 there. And there's the exact symbolic answer. And if I convert that to decimals, I think that's the answer I've got, is 17.501. That's kind of a nice problem, especially as you get ready here to do the AP Calculus exam. I don't know if we would see one quite this complex on the free response portion of the exam, but this one isn't too bad. This one is doable analytically, and I think we could score this one in a reasonable way. So you know me, Curtis, I got to try a picture. Here's what I produced with Mathematica. Tom might be able to produce something a little bit better. In this one, I was actually able to add, I think, the x-axis here, and I was able to color in over here. So this one looks more like a solid, I think. It's kind of hard for me to do this, take out that middle portion there. I couldn't quite do that in this one, but this at least gives you some idea about what this one might look like. Okay. Hey, let's try the next one. I like this one. There it is. So let's take a look at the curve given by the expression y equal the tangent inverse of x, y equals 0 and x equal 3. And we're going to revolve that about the line x equal 4. Holy Toledo, this illustration looks complicated. The region of interest is once again shaded in blue. This blue curve is y equal the tangent inverse of x. And I want to take this region and revolve it about the line x equal 4. Let me add in a little bit more. About the line x equal 4. Well, okay, as I draw in a radius here, as I draw in a radius at an arbitrary point, let's say y, I notice that that radius is perpendicular to the y-axis. So that's telling me that I'm going to have to integrate with respect to y. I also see here that the axis of revolution is not a bounding curve. So this is going to be a washer technique. I'm going to scribble a little bit off to the side here. I can see that r is perpendicular to the y-axis. So I actually write this out in my class. So that says to me this is going to be a dy problem. I see that this axis of revolution is not a bounding curve. So I'm going to have to use the washer method. So I've got to find an outer radius and an inner radius. I'm a little worried about this because I've got y equal to the tangent inverse of x. What the heck do I do here? Here's the outer radius. There it is. Gee, the lag time was a little slow on my screen there, Curtis. So how do I find that distance? So I guess what I have to do at an arbitrary point y, I've got to find this distance. So I have to turn around and solve this expression for x. So I can, in some sense, take the tangent of both sides. So the tangent of y is equal to x. So at an arbitrary point y over here, what's that distance right there? Well, that's the tangent of y. And what's this distance? It would be 4 minus that little distance in there to give me this. So there's the outer radius squared. The inner radius represented right here. Well, that's kind of easy. That's straightforward. That's always 1. So there's the inner radius squared. And wait a minute here. How does y vary? It goes from 0 up to this value. And let's see, where does that intersect that curve? Well, let's see. I've got y is equal to the tangent inverse of 3, right? I plug in an x equal 3. So y varies from 0 to the tangent inverse of 3, which looks very awkward. We don't usually see something like that. But there's my expression for the integrand. Now, I've got I've got 3 dots in here, and we'll leave a little bit of this for you to start or try with your class tomorrow morning at 8 a.m. when they come in. Just thinking out loud, I'm going to throw this out there, Curtis, if anybody answers in the chat, if they could just think a little bit and suggest how you might find an analytical antiderivative of that, what you would do, what the technique might be. When I did all of that and plugged in the bounds, strangely here, there's a natural log that appears. Excuse me, and that's the exact, I believe, analytical expression. There's the decimal approximation. And I did my best here to give you a visualization of what this solid might look like. So here's the line right here, x equal 4. Over here is the x and the y axis. There's the origin. And you can kind of see this y equal the tangent inverse of x as I rotate it. That region rotated about the line x equal 4. Now, I know what somebody's thinking out there. All these AP Calculus teachers that are really superb at instructing their students, preparing them for the exam, and giving them extra material. Somebody has taught them, many of you have taught them the shell method. And you might look at this and say, oh, you know what? This is an easier problem with the shell method. Well, okay. So let's see. I think this is the setup with the shell method. I think this is the setup where I think of as this is R times H times dx. So R.
Hey, Steve.
Go ahead.
I think you got somebody to take you up on your question.
Oh, good. How do you do that?
So the tan y term will have a u substitution with u equals cosine x. And
Good. Excellent.
There's also a tan squared y term.
Right.
Is the Pythagorean identity to get secant x, secant to the x. Is that right? Am I reading that right, Stephen?
I'm not sure about that.
I don't think I'm reading Pythagorean identity to get secant.
That's a little bit better. So what you use
secant squared. That's what I was. Secant x squared. That's what I was missing one thing there, and I got the. Thank you, Wanda. Got it.
Very good. So use a trigonometric identity on tangent y squared. Excellent. That's really good. I think that's a nice problem for your students. Super.
Now there's a few students who've got the solution.
There you go. That's right. All right. So I think this is the expression for the shell method. There's a 2 pi out in front, and I apologize for this, Curtis, but I'm going to go back up here to this figure just for a minute. If we're using the shell method, and my figure is going to get a little messy, here's a way that I think about this. I take an arbitrary value x in the region of interest, and what I'm going to do is I'm going to draw a line up to that bounding curve, and that represents the height of an arbitrary shell. And I'm going to draw a line perpendicular to that to the axis of revolution, and this is the radius. That is the radius of an arbitrary shell. And so what I need are expressions for those two variables, h and r, in terms of x. What's the radius? What's this distance? It's 4 minus x. And what's the height? In this case, it's just the tangent inverse of x. You might think a little bit about how you would integrate that analytically, if you can, but I believe that works out. It better work out to the exact same numerical answer, 35.426. We frequently get this question about the AP Calculus exam, Curtis. You know, if some students look at a problem like this and they say, oh, you know, this is too hard for me to do with the disk method. I can do it that way, but it's a lot easier with the shell method. Do they get full credit? And the standard response is correct mathematics receives full credit. But sometimes it has to be completely correct. And it depends upon the problem. It depends upon the chief reader. It depends upon the application. So can you use a different method? Yes, as long as you get it all correct. That's the general rule of thumb. So that's, I think, a tip as to why you should probably stick with the techniques that are on the syllabus. All right, let's try another one. Let's see if we can do this one. I like this one.
Hey, Steve,
Yes,
okay,
sir.
if I make an additional comment about the
Sure.
grading? So I think what I was going to point out too is these two calculations where you're working it out exactly, there's a lot going on in that ... But very often on the AP exam, these kinds of problems would appear on the calculator open part of the exam.
Correct.
And in fact, what the graders would want to see is basically that first equals all the way to that numerical answer, because they're going to assume that you've done it with a numerical integration on it. And in some cases, the AP exam might just ask you to set it up.
That's correct.
The out calculation. They just want to see, can you set it up? Because with a numerical integrator, it is just one button push once you have it set up correctly. So,
Yep.
Oh, back to you.
Excellent. Excellent. All right, well, let's give this one a shot. A little bit different. This is problem 2. Hope you got to this one. I hope Allison did this one because we might have a question for her. Let's let R be the region bounded by these two graphs. I'm going to stop there just for 1 second. I'm going to add a little bit to my picture. I think the blue graph here, after thinking about this a little bit, is y equal 4 minus x squared. And the green graph is y equal e to the minus x minus 2. So we're going to let R be the region bounded by these two graphs. And this is definitely a calculator active problem. And Tom, help me here. Don't let me miss anything as we talk about calculator tips here on the exam. I want to find the volume of the solid that results when we take this region R and we rotate it about the line y equal minus 3. So here's what I see. Lots of little things before I set up my definite integral. I've drawn these two graphs, and the first thing I'm going to have to do is to find these 2 points of intersection. So this is certainly a calculator active problem. I don't think I can find those points of intersection analytically. So I'm going to find these x coordinates of the points of intersection, and I'm going to store them to the greatest degree of accuracy that my calculator allows. I didn't put a calculator screen here in this presentation. We've done this a couple of times, Curtis, but I'm going to let A be equal to this value and B is equal to this one. So right over here, this is A, and this value on the x-axis right here is B. Those are the x coordinates where these two graphs intersect. So the region of interest, once again, is shaded in light blue, and I want to revolve this about the line y equal minus 3. I apologize, a little redundant here, but once again, this axis of revolution is not a bounding curve. So that suggests to me that what I'm going to have to do is use washers. So I've got to find an outer radius and an inner radius. I'm going to draw both of them in. I think you can see them. I've got them denoted there. I notice that both of these radii are perpendicular to the x-axis. So that says to me that this has got to be an integral with respect to x. And now I've got to find expressions for the outer radius and the inner radius. Here we go. Here's the pi out in front. A to B. And by the way, it's okay to use variables A and B as long as you write on your exam paper those actual values. If you don't do that, I would recommend that you write at least 3 decimals up here for A and B. But this is the better strategy, is to define your variables A and B, write them with 4, 5, or even 6 decimals, and then use those variables in further calculations, further expressions. Beautiful. What's the outer radius? Well, it is this distance from here to here minus, let's see, 3 minus a minus 3. So that's a plus 3. There's the outer radius. What's the inner radius? This distance. So it is here, that distance minus a minus 3. So plus 2, plus 3, excuse me. There's the inner radius. Boy, I hope I did that one. Okay, I'm going to do a little bit of simplifying here. I think I did this right. 4 and the 3, there's the 7 minus x squared. E to the minus x plus 1 squared. Yep, the minus 2 and the plus 3. Beautiful. And as Tom was saying, this is if this were a calculator active problem, that's all you'd have to do for the setup, and then go to your calculator and type in or get this answer of 332.826. As I think about this one, and maybe we can leave this one for an open question in class tomorrow morning, can you find an analytical expression? An analytical antiderivative? I think I could do that one. I'd expand out both of those expressions. I think I can do that one. And here's a rough idea of what this solid might look like. I know it's kind of skinny. I've got a couple of labels in there for the x-axis down below. And I'm revolving this about the line y equal minus 3. I believe that's this black line right here. This is y equal minus 3. This one represents the x-axis. That's not too bad. I guess you can see at least that open part. If I were to rotate this a little bit, I think that open part would become bigger as we look down through it. Go ahead, Curtis. I'm sorry.
Hey, Steve, we got a question that came in. If we labeled the top, the blue equation, f of x, and the other green g of x, could we just show the integral of f plus 3 squared minus g plus 3 quantity squared?
That is an excellent question.
Is that reasonable?
Yep, very reasonable. And in an AP calculus exam, it is quite likely that they would be already labeled for you. But if they're not, if a student comes off to the side and says, well, okay, I'm going to let f of x equal 4 minus x squared. I'm going to let g of x equal e to the minus x minus 2. Yes, perfectly acceptable to write pi, the integral a to b. Don't let me forget all my parentheses in here. This would be f of x plus 3 squared minus g of x plus 3 squared dx. And the truth is, Curtis, that's the preferred way to do it, because there's less of a chance of making a mistake, a copy error.
Right,
So
right.
Excellent question. And in fact, if this were a calculator active problem, in my opinion, I wouldn't even write this next step. I wouldn't even go to simplify, because I've got F and I've got G already in my TI-84. I'm going to go directly to the calculator now and get an answer to 3 decimal places. So that's a really good question.
Okay, good. And we had another question, but Mark took care of it in the chat. So
okay,
good deal.
Superb. All right, well, let's switch just a little bit and take a look at some other types of questions here. I'm sure you've seen these. You've been doing some of these. We have a solid S that has base R. Each cross-section perpendicular to the x-axis is a semicircle whose diameter lies in R. What's R? Well, notice this is part B here to number 2. So this region R is the same one we just talked about a moment ago. So up at the top here, this is y equal 4 minus x squared, and this green curve is y equal e to the minus x minus 2. This time, each cross-section perpendicular to the x-axis is a semicircle whose diameter, here it is, lies in R. Hey, that's not a bad picture. Can you see that semicircle, Curtis, kind of coming up from the paper? It's coming
Yeah.
up at you. Okay.
I had it going on the opposite side. I had
Okay.
in my
In
head,
your
but
picture?
sure, coming up
Okay.
from the paper, that's fine.
Okay. All right. I'm going to scribble just a little bit off to the side. When I introduce volumes in my class, I actually start by looking at these types of problems because I think about volume as being a definite integral from A to B of A of X dx, where A of X is an arbitrary cross section. And then that leads me into disks and washers, and in my class, even shells. But I generally start with this, but I know that many teachers don't. Many start with disks and do washers and then get to this part, and that's fine. That's fine. So, all right, I'm going to start out just by trying to find an expression for that cross section at X. So the cross-sectional area would be half the area of a circle. So there's the 1/2 pi r squared. So I have to think about, well, what's the radius? So the radius is roughly this distance. It's half the diameter. Can we figure out the diameter? Sure, that would be this distance from here to here. That would just be, well, f of x minus g of x, as defined on the previous page, right? So where this is f of x, and where this is g of x. So I have to take the diameter divided by 2 to get the radius, and I've got to square that. And now I'm going to try to simplify this a little bit if I can. So I think inside here, I've got a 4 minus x squared minus g of x. I did a little simplification here. There's going to be a 6. And there's an expression for the cross-sectional area. So I've got a pi over 8 integral from A to B, right? Because that's the little a and little b from the previous problem where these curves intersect. This is a calculator active problem. I wonder if I could do that one analytically. I'm not sure. I got a 21.714. That's a cool problem. I like that one a lot. Tom, I think I had an AP scoring point on this one. Did you have anything that you wanted to add here? Did we talk about that previously?
Yeah, I'm not sure. There was something I thought I would just illustrate that what you were mentioning about kind of best calculator usage here, if that was okay.
Sure, you want to? I'll stop sharing.
I'll keep it short, but try to
Okay.
All right.
All right, hang on 1 second. There we go. Okay, there you are, sir.
Okay. If I can pull this off. All right, so hopefully you're seeing my TI-84 screen here.
Got it.
And I went ahead in the y equals menu, went ahead and put in these two functions that you were dealing with.
Okay.
So I'm going to go ahead and graph those. There we go. Looks like a nice graph.
Cool.
But here you had a problem where you had two different parts. We're making use of those limits of integration, both of which are kind of messy decimals because they're intersections of curves that can't really solve the intersection algebraically. So when we're on the graph here, we can pull up the calculator. It's the shift of trace, and we can calculate intersections. And let's see, it says ask for a first curve. Okay, I'm on the blue curve. I hit enter. Second curve is the red curve. And I'm pretty close to that left-hand intersection point. So I'm just going to hit enter my guess there. And there's that nice intersection point.
Mm-hmm.
And so on my AP exam, if I'm a student, I want to write down, okay, that's going to be my A value. So I'm going to write down A equals negative 1.397781, like that. But then what I want to do next is I want to go to my calculator screen and just recall X. And there it is. Okay. And then I can store that right away into the value A.
Mhm.
And now I can actually, if I'm setting up a numerical integral on my calculator, I can use that value of A just like it is. And now I would want to do a similar thing, go back to the graph, hit my calc key again, do intersect. I'm going to move over. Whoops. Went a little far there. Let's see. Actually, right now, the main thing I want to do is just be on the blue curve. So I hit enter, second curve, red curve, hit enter. I'm pretty close to that intersection point. So I'll say that's a good guess. There's that second intersection point. And again, go back to my calculator screen, recall X. There it is, and store it in B. And now those things are, now I do want to write that down on my AP paper, right? That B equals this. But once I've declared those values, now in my calculator, I don't have to retype those in. I can just use A and B. And this was one where it was used in multiple parts. And I've seen those intersection values used in the 3 or 4 parts of this kind of volume primer question. Okay.
That's a crucial tip, Tom.
Oh yeah, it really saves time and it's accurate.
And it keeps you from making those intermediate rounding errors.
Absolutely. Yeah.
Correct. Yeah.
So that's really, really important.
All right, I'll stop the share and turn it back over to you, sir.
All righty, here we go. Beautiful. So there was a picture that I produced with Mathematica of what I thought this solid might look like. Not bad. Can kind of see those semicircles there. And let's take a quick look at this one. I'd like to take a look at 2 more here if we can. So this time R is a region bounded by these 2 graphs. Boy, those look terrible. And the lines x equal 1 and x equal 3. So, all right, I've drawn in this region. Let me add a little bit more notation in here, Curtis, just to make this a little bit easier. I think that I'm going to call that f of x. I'll call this g of x. And I believe this blue curve is, in fact, y equal f of x. You might think a little bit about this and why you can argue that the green curve is g of x. What happens when x is equal to pi, and I think I can see what's going on there. Between x equal 1 and x equal 3, so I think I can see that region. Find the volume in this solid, that results when r is rotated about the line y equal 1. Okay, so here's y equal 1. Once again, the axis of revolution is not a bounding curve, a good candidate for washes. I'm going to draw in my 2 radii. I note that they're perpendicular to the x-axis, so this is going to be an integral with respect to x. I have to find expressions for the outer radius and the inner radius. So let's see, the outer radius is this distance. That would be 1, y equal 1 minus y equal g of x, there it is, squared. There's the outer radius. Inner radius, y equal 1 minus y equal f of x, there it is, squared. Boy, that looks awful. I don't know if I could do that one analytically. But this is a calculator active problem for sure. The bounds are pretty easy, 1 to 3. When I plug them in, I got a 2.46. And strangely, I think I was able to produce a pretty good visualization of what this solid looks like. So this is actually down here, the x-axis, and this is the line y equal 1. And that's about what that solid looks like. That's not bad. I like that. And let me take a look at one more and we'll leave a problem open, Curtis. So we'll be in good shape here. So this is a part B. So we're still dealing with the same 2 curves. So this was our, I think, y equal f of x. And the green curve was y equal g of x. And this time we have this solid S that has base R. And this time each cross section perpendicular to the x-axis is a square. So with a little bit of luck, Curtis, you can see that square coming up from the screen. And we've got to see if we can find the cross section, pardon me, the area of that cross section. So what I want to try to do is to find the length, a length of that square right there. So what is that? Well, it's really just f of x minus g of x, isn't it? That's this distance. F of x minus g of x gives me this distance, that length right in there. So that's a side of the square, and son of a gun, I need to square it. So that's my expression for a of x. Calculator active problem, thank goodness. When I plug this into my calculator, I got a 0.142, almost a little counterintuitive, very, very small volume here. And this is my drawing here, Curtis, of what this looks like. You can kind of see the squares in there as I move across from x equal 1 to x equal 3. That's not too bad. Cool. So teachers, students, as you prepare for the AP exam, I'm not going to do this one at all in gory detail. I think this is just a really cool problem. It takes a look at all kinds of volumes of solids, of revolution. I've got one curve in there that is defined specifically. You may have to figure out some of the other curves, given some of the other clues in this picture. There are 3 regions that are defined here. If you can see this in color, there's a region 1, 2, and 3. And I'm asking you in this problem to find the volume generated by rotating the given region about the specified line. So for example, in part A, I want to take region 1, which is light blue, and I want to revolve it about the line OA. Where the heck is OA? All right, well, there's A, there's the origin. So I'm taking region 1 and revolving it about the x-axis. So given everything that we've done tonight, knowing all the formulas here for discs and washers, I think you ought to be able to do all of these. This is a great problem to get your students ready on a Saturday morning, to have them come in early and see if they can work this one. Great, Curtis, thank you very much. I really do enjoy this one, enjoy this topic. Any other questions in the chat that we can handle?
I don't think I've seen anything come in the chat tonight. You guys did a really nice job. I especially appreciated these problems. This is one of my favorites as well, just these
Cool.
visualization and trying to figure out what those volumes even look like.
Yeah, what those solids look like, yeah.
Right, yeah, what does that solid look like? What am I actually trying to find?
Yeah.
That's always a good and unique problem. So really enjoyed this evening, Steve. So thank you very much. Tom, thanks a bunch. Just a heads up to the teachers, I put it in the chat, but you can reach out to me at my email address, curtis@ti.com, and I'll send you a link for 1-hour teacher training certificate. And then also be watching the description. Steve's going to send me the solutions from tonight, and I'll make sure to have those teacher solutions up there in there tomorrow. Apologies for not getting that done as quickly for the 3-6 one as I should have. And then I'll post the questions for our next one. We'll be live again on Monday, April 3rd. Ready for our second to last session of the spring on Monday, April 3rd, 8 p.m. Eastern and 7 Central. So looking forward to it. We will talk to you guys in 2 weeks.
Thank you, Curtis.
Bye-bye, everybody.